7.2 problems. Will magnesium react with water to produce hydrogen gas? Well, magnesium means the solid, so we have the solid. It could turn into the cation. So here's one thing it could do. And then we're going to need water reacting. And I know this has got to be the oxidation because you are not going to be putting electrons onto solid metal. So if we're starting with a solid metal and it's the only solid metal available, it's going to be doing the oxidizing. This will be losing electrons. We'll find the reduction potential and turn it around, which makes this a positive, it turns out, when you go and look on your standard cell potentials, which means that water has to be doing the receiving of electrons, the reduction. And it turns out that's a negative value of voltage for E standard, E naught. And when you add them up, though, you still get a positive voltage, and that makes it still spontaneous. And this is still true. It will still happen. That repeats all the way through E, that same concept, and I'm going to go on. So consider this cell below. We've got solid aluminum, aluminum ion, solid zinc, zinc ion. One of these has got to oxidize and give electrons, and one's got to receive them. They are in the standard condition. I would write this down. Standard conditions are 1 molarity. And I think 25 degrees Celsius, not that that's going to come up at the moment. C7.1 lesson and problems for further discussions of why the salt bridge and so forth. So we go and find our E naught values for the reductions, and one of these has got to turn around though. Well, it turns out that that's a negative and that's a negative for the reduction values, but one of these has to turn around. Something's got to give the electrons and not just receive them. And if that's a negative and that's a negative, I'm going to turn around the one that would make the biggest positive. And that's what nature would do. Remember, it's going to achieve the overall reaction that gives a positive E standard voltage or standard cell potential voltage that is positive. Remember, the test won't say E naught. It won't say E standard. It will say the standard cell potential. So if I turn around this one, I get a positive, and then I still get a positive when I add them up. Now for the overall reaction, this one wants to give take in 2 electrons, notice zinc +2 to zinc 0, and this one wants to give away 3 electrons, Al0 to Al +3. So we're going to multiply this line by 2, this line by 3. That way the electrons cancel out, and that's very key. The electrons need to cancel out, and they do not appear in the overall reaction, and that's how we got the 2s and 3s here. For 2b, I need you to follow this because they expect you to be able to get from this formula, if it's provided, if they're going to use it, to this one if they want you to solve for k. So you may have to hit pause and copy this down and have a long think, but here we go. This is the energy of the cell in the current conditions measured in volts. This is the standard conditions volts. And it's minus the R constant. You're going to need the one with joules in it because there's joules in volts, the temperature in Kelvin, the number of electrons being passed in this overall reaction, Faraday's constant, which will convert between moles of electrons, which is what you've essentially put in there, and coulombs, because inside volts is coulombs. And this is natural log of Q, which is the K math in the current conditions, is the snapshot K. I want to solve for K, though, not Q. And if K is true, that means that the system, by definition, is at equilibrium. And also then, the current cell conditions would have no volts. The system, by definition, at equilibrium wants to go neither forward nor backward. It has no voltage. It wants to go nowhere. This is 0, which means I can subtract this over here. Now I have 2 negatives. I can take them off. Also, I divide this under here, which gives me this. The bottom of the bottom is the top of the top, so I'm going to move that up here. And our special little trick, to undo natural log, we're going to take E, Euler's number, to the power of both sides, and when we do it on the right side, it unzips the natural log and it simply disappears. And now we have the formula that will solve for K if we know E standard potential. So we have a formula that solves for K. This is our voltage. We found it up here. This is the moles of electrons used per mole of reactions, or it's the ratio of electrons used per one reaction. This is Faraday's constant. It was rounded off in this case by someone. Here's the R value, get the one with joules. And the 25 degrees Celsius standard conditions in Kelvin. Multiply, divide, and get a value. Do inverse natural log or shift natural log or second natural log or whatever you got to do. And we get K, and it's freaking huge this time. For C, we need to have a bit of a math think. Now, Q is products over reactants to the power of the number in front for the current conditions. Now, very much remember that standard conditions that generated E naught or E standard were 1 molarity each for the cations, and the aluminum is the product cation and the zinc is the reactant cation. So it's the aluminum over the zinc, and they originally at standard conditions were 1 molarity each. So if we made the aluminum to be 2 molarity, the numerator is going up, Q is going up. And if we look at this formula, let's see what happens to the current conditions E value. What are the current volts? If this number goes up, ln of Q goes up, which multiplies this to be a bigger number. And then notice we're subtracting a bigger number out of our standard potential, which means we're getting a smaller answer for the current conditions volts, which does stand to reason. As you run this reaction forward, does the cell get more powerful or less? And I know that joules are not power, technically that's watts, but does it get more energetic or less energetic as the reaction runs forward? And it has to be less, right? And I say that because you could alter this molarity like we did. We just alternate because we felt it like it. Or I want to also point out, as the cell runs forward, the products increase and the reactants decrease. So as the cell produces electricity, the numerator is going up, the denominator is going down, and this thing is sort of headed to infinity, with the limitation in practical terms, though, that it can only hit K. Now, I know K in this case was huge, but it doesn't have to be that big. But this ratio, don't forget the exponents, the answer for Q can only proceed until such time as it hits K. And when K is true, you will have hit the point where the current volts are 0, right? Why? Because the ln of K times this will be that. This whole thing is set up such that when you take the value of K, take natural log of that, multiply it by this, you will generate the same value as E standard, in which case you have E standard minus E standard and you get 0, which is what we said before. At equilibrium, when K is true, the current conditions voltage is 0. Well, of course it is. At equilibrium, nothing's going to happen. There's not a voltage or a potential to go either direction. So if we made the denominator greater, we would get a smaller Q, and with the converse of all the logic I said before, the potential would go up. In fact, what you want, in a certain sense, is very little product ion, because what you want is lots of room in the cell to make more ion. You're going to be making more of this. Don't put a bunch in. Don't pre-stock your solution with this. Leave lots of room for the new ones. Otherwise, you're just getting in the way of yourself. On the other hand, this is, so to speak, fuel for the cell. You need lots and lots of this. So what you want is very little product and lots of reactant. So then you have a numerator that's very small, a denominator that's very large, and you want Q basically as small as possible. You want it far and far and far from K. We said this reaction is going to run until such a time when the value of Q hits K. Well, you want that to be a long time, don't you? You want the cell to last a long time and provide electricity for a long time. So there are two things you can do. You can change the ratios so that there's much, much, much denominator and very little numerator. And what that can do is affect the current voltage. because the Q value affects the voltage. That's what I was saying before. Also, though, there's a different aspect we could consider, which is the total energy of the reaction available, the total reaction over the life of the cell. The total energy, not just the voltage, the total free energy. And the total energy, not just the current voltage, would be affected by making more and more chemicals. So it does stand to reason that a bigger battery with more chemicals in it will last longer. Why? Let's just say I'm using 100 electrons per second, just to pick a number. Well, if our reactant cation here can accept 10 million overall, with all of them considered, then it's going to take a lot longer to run through all the chemicals than if they could only accept 10,000. More chemicals is going to be able to run longer and pass more electrons. So the current voltage is affected by the ratio, so you might as well make that small and that large. But the overall cell life and the number of electrons it can pass before it goes flat dead will be affected by the number of cations in there, which means a bigger battery will last longer. And once again, it will run until such a time that it hits K. This number will increase, this number will decrease, and at some point, you must hit a value, use the exponents, that K is true, and at that point, there is no more current voltage in the cell. On D, there's not a lot of trick to this. They want the current value, the E cell voltage, and we know that reaction, but we do have a whole lot of information. We don't know Q, but they told me molarities, and we know the exponents from back in part A. So we're going to put in the molarities, use the exponents, divide, and get Q. Put Q in here, natural log, go fetch all these numbers. Remember, that's a 6 for this reaction because we went and figured that out up in A. And multiply and divide, don't forget to take natural log. I would take that separately, possibly, unless you're absolutely confident of your calculator, because I've had calculators do things I didn't expect. And then we have the current voltage. On 3, we have a situation, we have copper metal and silver ions. Okay, so it must start with the copper solid. That has to be the oxidation. So we go and look up the value. Turns out it was positive, but now the sign has to change because we're going to flip this to oxidation. Instead of reduction, which it was presumably on the table, the cation, of course, is going to reduce. It's going to accept electrons. It's not going to go more positive and lose electrons. Plus, we know that one's got to be the oxidation part. So we'll keep the reduction value, which happens to be positive, and we add them up, and it does, of course, go down because I have a negative, but I still get a positive overall voltage. This E standard potential shows me this will happen. You will get a reaction if you just stick copper metal into a silver ion solution. The electrons already cancel out, so we don't need to multiply by anything here, and we can just cancel them out and shove the whole thing together for the net ionic reaction. So is it spontaneous? Yes, because we got a positive value. I already showed you how to solve for K. Here's delta G, though. So we just found E standard up top. We can put that in. And if you want to show it this way, remember a volt is a joule per coulomb. And it is kind of nice to show that because then it shows why Faraday's constant works. And I know that this is the rounded off version, but you can look it up in the booklet. The coulombs cancel out the coulombs if we write joules over coulomb. So we get moles of electrons canceling out, coulombs canceling out, and we get joules per moles of reaction, which is what we said back in chapter 6 are the units for delta G. And if you put in E standard, you get delta G standard. Also, if you put in B cell, you get delta G current conditions. Also, remember that the fact that this was a positive number means that this reaction likes to go forward. Nature favors this reaction. So we know that our delta G value needs to be negative. That's why there's a negative here, and everybody has managed to forget that at some point. So remember that there is a negative, and that's because when this is a positive, this needs to be a negative. Negative delta G is a favored reaction, but positive voltage is a favored reaction. On 4, we have two half reactions. One of them's got to be oxidized. So flip the one that's going to give you a positive voltage and then shove the two together. It turns out we have 2 electrons and 2 electrons, so we don't need to multiply, and we have an overall reaction. Delta G is no problem. I know that that's 2 moles of electrons. F is given to me. You can write that as joules per coulomb if you like. Make sure everything's canceling. I multiply that sucker through. Make sure to keep the negative, because if that's a positive to show us it's a favored reaction, then that is a negative value. I already showed how to generate this formula. We know E standard, we know N, again, that's a repeat here. I know Faraday's constant, that's a repeat here. Again, this workbook likes to use the rounded off value for some reason. That's R, make sure to get the one with joules. And this is standard temperature, 25 Celsius in Kelvin. Multiply, divide, get an exponent on E, inverse natural log would get you K. So on C, we're gonna introduce new conditions, new molarities. Now, something I would make sure I understood and wrote down is at standard conditions for these things, molarity is 1, and let's pretend these are all 1 then Q is 1, isn't it? The current conditions at standard conditions, Q for standard conditions, with all these being 1 would be 1. We'd have 1 divided by 1 divided by 1, and we get 1. So let's repeat that. At standard conditions for a galvanic voltaic cell, Q is 1 by definition. That's in the definition of the term standard conditions for this. So we're not at standard conditions, and our numerator has grown. And we also just had a big discussion that if Q is going down, the current voltage is actually greater than it was before. A smaller Q gives you a bigger cell potential in your current conditions than whatever you were discussing before. Well, what I was discussing before was E standard. I'm comparing the current conditions to E standard where Q is 1. Q is less than 1. Now, then that means that my current voltage now is greater than my previous conditions, E standard. So what would it actually be? Well, I know Q because I just found it out, put it in here, find R. That's still unchanged, I believe, 298K. This is 2 moles of electrons passed each time. Get the unrounded version out of the pamphlet. ln of Q, multiply, divide, maybe write down Q first, make sure your calculator is working. I would really, really make sure that you know how to string this together if you insist on it. Get the answer a couple different ways. Make sure you know what it is and you're confident of it, and then see if the way you would like to type it in actually produces the same result. On the free response, we have this solid and cation versus that solid and cation, and one of them's got to be oxidizing and one of them's got to be reducing. So we'll look up our reduction potentials in the standard table, and we find out that we have 2 negatives. Well, let's turn around the one that will give us a bigger positive so that when we add them up, we get a positive voltage, because that's what nature would really do. It will run in the direction causing the reaction that will give a positive voltage. And I know they only asked this down here, but that seems to be out of order to me because I don't know which one to turn around until I consider that fact. Which turn and change of sign will give me a positive voltage in the end. Anyway, that tells me to turn this one around, and then I can get this positive voltage here. The overall balanced net ionic equation, though, will be when the electrons cancel out. This is using 2 electrons because I've got a +2. This is using 3 electrons because I've got a +3. That's why I have to multiply this line by 3, this line by 2 from the previous versions. I know they already did it in here. You can check the reduction reactions shown in the table if you like, and you'll get 3 electrons and 2 electrons. But after we multiplied them, then we get this. Now the electrons cancel out, do not appear in the net ionic, but everything else does using these numbers. So what's delta G standard? Not that hard. This is the number of electrons exchanged per reaction. Essentially, technically, it's moles of electrons per moles of reaction. Look up Faraday's constant. Again, they keep using the rounded off version. Volts really are joules per coulomb, and I got that back there. This is E standard. I just found E standard. multiply that sucker, make sure you get a negative value. If this is a positive voltage, then delta G is a negative value because it's positive voltages and negative delta G values that are favored reactions. That's why there's a negative there, to make sure that you get a negative in your final delta G answer. In B, we're going to change the molarities, apparently, I guess just because we feel like it. So if we check back up here, Sn plus 2 is the reactant cation. So the reactant cation has gone down by a factor of 100, which means the denominator has gone down, which means we're going to get a bigger Q. And conversely to the way it might seem, but I did explain it, if Q is going up, E is going down. So if this is going to go down and give me a bigger Q, the current voltage is smaller than the previous, or E standard, because that's what I'm comparing it to, voltage. And one more time through, if this is going up, then ln of Q goes up, which means this whole thing goes up, which means I'm subtracting out a bigger number, which gives me a smaller answer than I used to have.